Last night I was up pretty late trying to turn some of the data from Denmark, very fresh data, into that is already tiled and a little bit processed back into sort of raw data like you would get it when it's raw. So you can just take this folder and put it right next to Denmark. Now logically you may want to put it inside of Denmark, but that would make sense. But for the purpose of this exercise, it's more convenient if it's next to Denmark. And then you will basically be able to find it afterwards in the LasTools bin folder. It will just be below Denmark. And this is the data we'll be using all day long. It's a bit more data than I was planning to, but it's quite nice data. So I hope we'll be able to learn all the concepts of a processing pipeline. Maybe let's use LasInfo. In the Isenburg folder we have a strips raw folder, and now we have these lines which are numbered. These are the numbers I found in the vendor was providing these lines with these particular numbers. And if we load them, you get these flight lines here. And so I remember when I want to look at only one file, I have to choose selected file only. And then for example, I pick this one here at the very corner. I say view. And this should be very familiar by now. And I press start, it will start to view that data. And now, after looking at Poland and at the US yesterday, we're finally looking at some, and also very fresh LiDAR data from Denmark. Let's exit this file and run a tool called LasIndex. It's right above LasInfo. LasIndex is right here. And if we run LasIndex, we have a tool that creates these LAX files we used yesterday. These are useful because if we want to explore the data, it allows us to load pieces of the file faster by having a spatial index that tells us where in the file we need to go to load a particular set of points. And this is something you have to do once in the beginning. Here I'm going to my raw strips, I'm adding them all, and then, oh, there's a new option. It's actually a new option. And let's try out the new option. I just recently added this, and I think you're the first workshop where I can try this now. Instead of creating these LAX files externally, there is now the option of appending them to the existing raw file. That's all you need to do. Oh, and maybe run on more than one core. So we have only 4 tiles. I'm running on 4 jobs. You should only run on 2 jobs. You should run 2 jobs. I say run. And this is the command line you should have. So all this will do now is add a spatial indexing to the 4 strips. What has changed? Well, if I now load one of these files, I should have a spatial indexing behind it. View selected file only. And now I say view. How do I know if I have spatial indexing? Well, if I had spatial indexing, then I should be able to see the spatial quadtree. Yes, it worked. So now we have suddenly a spatially indexed file. Before that, well, I should have done it before and after. So before this blue tree didn't come. And now if I ever do a spatial index query, and I want to read only this box here or this box here, it will read only parts of the file. let's look at one more of these. And I don't know if you noticed, but these files look kind of funny on one, always at the beginning, at the end, they look a little funny. You notice the difference between here, then here, and then here again. My most returns are below the aircraft, but as I get to the edges, it becomes more and more sparse. And yeah, well, we're not really so much interested in the water, in the scanning of the water surface. The important part is that we have all the returns on the land. What I want to do first, I want to create an overview image. And for this, we will use a tool for which you do not have a license, because I didn't license it as part of this exercise. But I think it's one of the crown jewels in LasTools. I haven't really advertised it much. It's called LasTools. And when I talked about LasTools yesterday, how I got started creating this streaming triangulation pipeline, that's exactly that. LasTools implements a streaming triangulation pipeline that can triangulate billions of points without any cuts in a seamless manner. One reason I didn't include the license for this tool is so I can also show you what happens if your license expires, or that you can work with LasTools for academic and research purposes, even if you don't have a license. I want to show you the kind of limitations that you will have. So the most annoying limitation is this box. But this box you only have when you use LasTools in the GUI. Eventually, when you start using LasTools regularly, I would expect you to write batch scripts. And in batch scripts, there is no pop-up window. There will be just a little message displayed when it's processing that says the same thing, but there's no more button to click. You need to accept this license, otherwise you can't do anything. And then everything works like before. The only thing difference is down here it says now unlicensed. But if you read the license, and you can read the license here, it says for education and evaluation purposes you can use and test LasTools as much as you want to, and then it goes into great detail, which is a completely free tool, completely free and open source, and which tools need to be licensed for commercial production use. So let's load these 4 strips again. 1, 2, 3, 4. Oh, now you notice the difference. I have LAX files, so I get these boundaries, which show me areas where I don't actually, there's no LiDAR points in this area here. So you get these slightly more tight bounding boxes. But again, yesterday we had east-west strips that were almost completely filled. Now we have north-south strips. If we had a diagonal strip, this would really be much more visible how this tells you where the data really is, because these boxes are almost full again. LasTools can generate very large rasters in a seamless manner with up to one. Why does it say Southern Hemisphere? So last night at 1 a.m. I put in the wrong projection information. I basically took Denmark, with one button click I moved Denmark into the Southern Hemisphere. Aren't you happy now? Oh, nice, warm, So we will need to fix that, but that's fine. At least we have a new task because we have a wrong projection information in here. I'm glad I saw it before we opened it in Google Earth and wondered where it ended up, where it went. So we can just override the projection information later. Actually, not later. Let's do it right now because we will use it by picking UTM 32. Northern. So I just typed in 32N. I wanted to type. I typed M, and I thought, oh, M is still northern, but I guess it wasn't. We will create a hillside shading because we want to get a visual overview of what the data is that we're looking at as an initial, because we just received the data and we want to know what is in this area. Maybe we use a step size of 2 meters because it's just for an overview. We don't want to be too detailed. We don't want to create too big of an image. The output should be an image format like PNG. You know, that's my favorite because we're creating an image and not an elevation raster. We want to merge them all into one because that's what LasTools is good at. You can merge many files into one and still raster it as one big file. And I want to keep the first point because I want to create a DSM. Because these points are fairly dense, and I'm rastering on 2 by 2 meters. I take one raster, so there's no point in keeping too many points around. So I'm only keeping 1 point for every 1 by 1 meter. So in the order here is very important. So first I keep only the first returns of every shot. And then of all these first returns, I only keep for every square meter one of them. So I will have in the end one first return per square meter, and these will get triangulated, and then I compute a 2 meter DSM from it. So there's no point of keeping all of the first returns since I'm going down to 2 meters anyways. So having, and it's just what I've sort of found. If I keep 4 times as many points as I have the resolution, maybe if you want to be on the safe side, you could keep even more. You could keep 16 points for every 2 by 2 meter to compute this triangulation. And now I say run, and look what command line I created here. Well, first one I already see I forgot to specify the output directory, so I say cancel right away because it's easier to specify that here than to type it. The output directory, I put it right into this directory. Into the Kalundborg directory. And I also want to name it a little different. I call it dsm.png. And in the background, that's why I always go, in the worst case, you can always type whatever it's missing or fix it by just modifying this line. So we have these 4 flight lines. We're merging them into one. If you don't have that merged, it will create one DSM for every strip. We only keep the first ones and then thin with the grid. So I told you before, we keep the first returns, and then for every square meter we keep one. Now it's very important that these two are in the right order, because if they are not in the right order, if you do first thin with grid and then first only, then it can happen that you have lots of areas without any points. Because thin with grid keeps whichever point comes first into a grid is let through. Now if that first point is last return, it takes up that slot. But in the next step it would get filtered, and then you will have a 1 square meter without any point. Then I'm rastering with double the resolution of the number of points I'm letting through, and I'm hill shading it. I'm outputting into this directory with this name, and I'm overriding the faulty projection. So what happens now, it reads one flight line after the other and creates in the streaming manner this DSM. The nice thing about LasTools, it can handle up to 2 billion points. Now 2 billion points is a lot, Sounds like a lot because we only have been working here with a few million points. But big survey companies or big project easily hit the 2 billion mark. I want to have a look at the output I created. That should now be in the Isenburg directory. And here it is, and it created a KML, and that should now be in the right place. The data originally did not have projection information. So they just named the file what the projection was instead of putting the projection information correctly into the file. Why? I don't know. It's a very simple addition with LasTools. So voila. Here we are. Looks like we're in the right spot. It lines up nicely with the Google Earth imagery. Again, don't think Google Earth is a truth, but to make yourself feel a bit more confident that you, for example, you landed on the northern hemisphere. So you very quickly will notice if you create this and you use a projection information and it is southern hemisphere that you are in the wrong place. So these are 4 different flight lines, and you see they are we don't see any. If flight lines don't match up, you often already now see artifacts especially if flight lines really don't match up, like if there would be a 1 or 2 meter difference between flight lines, that would turn into a 1 or 2 meter wall, between flight lines in that hill shading image. But so far everything looks good. What you also see, also this was unlicensed LasTools. This is the unlicensed version. Well, nothing really bad seems to have happened. If you add even more points, and I was hoping it would happen, but it didn't, eventually a black bar comes across it. And your workaround then is you make smaller tiles and do a tile-based pipeline. And at the end, you can use GDAL, an open source tool, to put all the rasters back together into one, if you want to have one big raster. But that's just to demonstrate you that even though there are license restrictions, it still produces results that most academics and researchers can work with. So what I want to do today is basically create an entire processing pipeline based on this data. We don't do the quality checking because we did that yesterday on some other data. Also, I don't have control points for this area. But if you want to do the quality checking, you have the data, you can do it as an exercise later. I would like you to create a number of folders now that we will use in the following. And I'll create the folder right next to the strips raw folder. And so we're going to call them new folder. We kind of call them, and then you sort of already will know what we are about to do. We call them tiles raw. Then the next one we call tiles ground. And I always put an underscore in there, but if you want to name them slightly different, that's okay. And then tiles classified. And then another one we're going to call tiles normalized. This will all contain LiDAR. This will all be different products, different versions that are more and more processed from the raw LiDAR. And afterwards, we will create derivatives and that will be called tiles DTM. Tiles DSM. And tiles CHM. So the three products we want to generate today, well, DTM and DSM I explained. It's a digital terrain model and a digital surface model. And the CHM we looked at several times as well yesterday. That is the canopy height model, and that's very useful in forestry. So we have our work cut out, because for the moment all these folders are empty and we want to fill them up. Right now we only have data here, and we want to get data into the tiles raw folder, so seems like it's time for tiling. There's a tool called LasTools. So I would like you to find the LasTools tool. Now I should go back one zoom level. LasTools. And let's just load in our raw strips. And this will be the last time we play with our raw strips. From then on, we do tile processing. So strips raw, load them all in. You already see a suggested tiling in green. It is 1 by 1 kilometer tiles, and I would say we just leave it at that. 1 by 1 kilometer tiles seem to be reasonable. The tile size you could change here. I change it to 500, for example, and then you have much smaller tiles. It's at 1000. 1000, that gives us 1, 2, 3, 4, 5, 6, 7, 8, 9. Well, this looks like this will be mostly water, but okay. We also want to put something, and that is, I mentioned it yesterday, the buffer. A buffer between tiles is necessary in order to avoid edge artifacts when you do computations along the boundary. Remember yesterday we had to fix a building because it was misclassified, and that building was right along the boundary. Along the boundary, bad things happen because I missed the information on the other side. So by adding a buffer, I'm basically making the tile bigger than it really is. I'm moving the boundaries away from the real boundaries, so the arrow will be along those boundaries. And at the very end, I cut off these boundaries again. So then the data should be correct all the way to the edge after cutting it off. And here you see the boundary, the buffer. This is how it will look, and a 25-meter buffer seems reasonable for this scene. The buffer should be at least as big as the biggest building in your scene, assuming the building sort of falls right onto the tile boundary. And I think that the 40-meter building in there, but I hope it doesn't fall right onto the boundary right now. But even the half the building would then be in the buffer, and things should go well. Another thing, it's nice to name your tiles something interesting. The default will be tile, and everything will be called tile. Now when we started in the Philippines, the first project, okay, we called it all tile. That was the first river basin. But after the 23rd river basin, there were like files and folders full of them. And then you find something, it's called tile. Well, it could be any of the 23 river basins. Had we given it a short acronym like, Pampanga or just something that indicates for you which river basin it is, it would make it much easier because you don't have to open the file and look at the contents to know where it belongs. All right, so I'm gonna call it Kalu. Kalu.laz. So all tiles will have this base name. And we want to specify an output folder, and the output folder should now be the raw LA, should now be the raw tiles raw. So I'm going from strips raw to tiles raw, and remember one more thing, we have the wrong projection in here, and now is a good time to fix it. So now we can override that projection with the correct one. So you just again go in here, UTM 32, and then every tile will have the correct projection and you never have to worry about it again. So I'll make one final pass over this here. And now we're looking at the command line. So the tiling is usually the first step you do when you have a lot of flight lines. We're tiling our 4 flight lines. I mean, that's not a lot. Usually you may have 50, 100, 200, or you will have very long ones. These are 4 rather short ones. This is a base name. We use a tile size of 1,000, a buffer of 25. This is a very important one. This will tell each point that it's from a particular flight line. This is the output directory, and we want to override the current projection information with this one. And then looks good, so I press start. And if I go now to the tiles raw folder, I should already see how the tiles slowly get filled up here. And now it's 4 tiles. I'm expecting 9 tiles in the end. Yeah, slow by slow they're filling up. So as the points are red, they are put into the right tile, and all the tiles are written simultaneously. All 9 are written right now. And last tile is done because the little window disappeared. Another way to check if these menus become active again, then it's also you know that the processing has completed. Okay, so we don't need last tile anymore. We have our tiles here. And let's look at one of the tiles. I can just double click to look at them. If you double click, you probably get something coming up. Which program do you want to open this file? And then you can, that would actually be a useful thing to do. Now I don't know how to revert to the scenario where I have to go through that operation myself, because you see my LAZ files are usually always opening with last view. You know, when it asks you, do you want to browse for a program? Then you say yes, and then you browse for last view. And in the very end, it asks you, do you always want to open programs with last view? And you should leave that button checked. And from then on, all you have to do is double click it, and the last viewer will automatically open. In this tile, we have 2 flight lines. If you step through the different visualizations by pressing C, or you can go color by flight line, you can see the 2 flight lines. And if I press 0 and 1, 0 and 1, I can still have information about which flight line is which flight line. Now, if you happen to pick a tile which has only 1 flight line, then you only see either green. Yeah, then you only see green. But let's move on to the next processing step, and maybe then you see, then you have your viewer right there in case you didn't manage to open it right now by double clicking. So the next step, we have our raw tiles, is to classify the tiles. So, but to classify, I should be more precise, to ground classify. So don't open last classify, that's for classifying the more complicated things. We just want to classify the ground points at this point. And the tool for that, you know from yesterday, is last ground. we go into the directory called Kalundborg. And now we don't start with strips raw anymore. Now we go to the tiles raw. And there you should have 9 files in there. So if I load these tiles, I see these tiles here. And you see there's overlap between the tiles. The overlap is 50 meters in total, 25 meters from every tile. And now I want to decide how do I ground classify this. And now it's a good idea to know a little bit about how big structures are in your data. What's the biggest structure in your data? Maybe if you know your data, you can maybe already decide now if you have houses or anything in there. Otherwise, let's just do a quick visual inspection, or not like this, selected file only. So I'm viewing the center file now to get a bit of an idea what I can expect. Oh, there's a house here. So I looked at the data yesterday a little bit. I think this is one of the biggest houses. So let's see how big the house is. I press X and I focus in on the house and I press X again. Oh, and it's right in the buffer. Lucky me, but that's fine. It's when we have the. So how can you measure the size of the house? Well, let's measure the width of the house. I'm making with plus, 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 or rather equal, 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 or in the menu here, points large. I make the points a little larger. And then I'm just picking one point on this side of the house by pressing I in the menu. And then I'm moving over to the other side of the house and I'm pressing I again. And you see the point that I picked right here. But more interesting is what happened in the black window. Because in the black window, it now also calculated the distance between those two. So that house is 20 meters wide, roughly. Because the XY distance between the 2 points I picked, and I picked them on both sides of the house, is 20. Okay, so I have 20 meter wide houses. Now I need to go into my settings here. And maybe I should read the README file. Okay, because that'll tell me something what those settings mean. And for cities or warehouses, the step size is increased to 25 meters. Oh, that sounds about right. So 25 meters suggests if something is no bigger than 25 meters, it should get removed. And the 25 meters here means the shorter side. So minus city should be the option I want to choose here. Not my favorite option for such a scene, but we have one really big house, and I hope we don't lose too much of the detail along the coastline. So I choose city, and I also choose ultrafine. I also want to compute the height at the same time. This is something that you can only do in the licensed version. Yesterday we were running last height separately. That's a pre-processing step for the classification. It computes for every point how high is it above the ground points. This tool computes the ground points. And when is it outputting it? As it is outputting the points, it quickly computes, well, I know where the ground is, now let's also compute how high all the other points are above this ground. Remember, I use this in order to later specify what is a building and what is not. For the building classification, I'm looking for points which are 2 meters above the ground and form a plane with their surrounding points. That's why I need the height above the ground. In the unlicensed version, you need to do this in 2 steps. You need to first run last ground and then run last height. Not a big deal, but good to know. Now I want to process all files. I want to process on all cores -1. You should run on 2 cores as always. And the output directory, as you, without too much thinking, may be able to guess, tiles ground. Did I forget anything else? Looks all good to me. Oh yeah, one thing, look, if I look at the projection, it's now fixed. It now says Northern Hemisphere in these tiles. So wasn't so hard to repair. I say run and I review my command line again. Last ground, list of files. This time the list of files are these tiles raw, all 9 of them. I run on 7 cores, you should run on 2 cores. I use the city option, ultrafine, I compute the heights, and I output it into this directory in compressed format. Okay, let's start. This will take a little while. So if you're done, then you should have now in your directory called tiles ground the exact same 9 ground tiles. And I'm not going to even do the double clicking since I'm not sure you can all follow that. I'll go straight on to the next step, which is last classify. Okay. Just making sure the folder's empty. Last classify. So now I'm starting from the ground classified tiles, which have also hopefully have the height information. I'm loading all these tiles. Here they are. I want to quickly check, do I have ground information? Do I really have height information? How can I quickly check that? And I'll show that to you as a little trick because I don't want to start last info now because it's another tool I have to start. So instead I start last view and I say cancel. I start last view on 1 file only. And now I do some command line programming instead again. I change last view to last info and I write at the very end space minus histo, and the height should be stored in a variable called user underscore data, and we did that yesterday too, and it's stored in decimeters. So if I use 10 decimeter bins, it gives me the height per meter. So, and I just want to check if this user data value has interesting values in it. Otherwise, I don't even need to start my last classify because it requires this data to be there. And the output will now go into the black window. So I go to the black window and voila, I see that the user data has a nice histogram with most of the points are at between 0 and 1 meter, 1 and 2 meter, 2 and 3 meter, 3 and 4 meter, and so on. So yes, I can also see that here by looking at the user data field. It goes from 0 to 255. If you looked at the last info report, before the last step, it would have gone from 0 to 0 because this user data variable was not used yet. This is just a little check, a little sanity check to make sure the next step makes sense because the next step will also take a while and I don't want to start it if it wouldn't produce the right output. With last classify, I'm not going to touch any of these parameters. I leave them all the same. The only thing I do change is the output directory. And as you can imagine, the output directory will be tiles classified. And I didn't change anything else. Process all files, run on 2 cores for you, output directory, and run. Let me verify the command line. Last classify, I'm running on 7 tiles, or on 9 tiles. Here are all the 9 tiles. I run on 7 cores. I output them into this directory in a compressed format. And I say start. Or maybe we play a little bit with manual classification while we edit. So let's go to last view, because we haven't really, I teased you a little bit with the manual classification initially, but we haven't really done that yet. Now that we computed the classifications, last view is a good tool to verify them and maybe fix them up a little bit if they are wrong in some places. So with last view, we're going now to load in the classified tiles. And maybe let's start with a smaller one, this one here. Selected file only, and view. By the way, oops. Here you can always see a little preview of what we did. So we run, for example, this file was generated by LasClassify, which was run with an academic license. It has 6.2 million points in it. That's a good thing to know, 6.2 million points, because if we want to do editing, we need to load all the points. Right now we will only load 5 million. And later when we want to edit and save it, it will complain that you didn't load all the points, so I can't do editing. So we should load at minimum 7 million points, so we have them all. The editing was a recent addition to LasTools, that's why I haven't automated that. I could just simply reload them. But right now it just prints out a warning. So I'm viewing the file. Oops, no, I already did that. So I need to cancel. You see, if you have that window in the background, it will tell you, if you want to start it again, you need to cancel the current start window first. So let's try it again. View. You should get this start window. Start. So that's our classification. If I say ground, what has happened? Well, here we have a typical demo effect.
But you did choose city.
Yeah, no. Yeah, I noticed yesterday when I was processing this data that it had a very particular setting for noise. I told you this. Repeatedly, there were points that were like 2 meters below the ground. There were noise points, and there were a lot of them. And they filtered them out in an initial step. I had never seen this kind of data set before, where you have so many little noise points just 1 or 2 meters below the ground, in regular, all over the place. And they used a special software or a special setting to filter out these noise and classify them as noise before they did the ground computation. Because what you see here, you have so many of them that they have turned into the ground. So if you look at the points that are brown, you see that these noise points below the ground surface have become the ground surface. Because, as I explained yesterday, the algorithm, I'm looking for points that are below the ground. And if I have a lot of noise points, and all these noise points are below the ground, then they're sort of forming a surface, so that all the really ground points are actually considered to be above the ground. So that's actually a very bad example for my algorithm, because we have lost a lot of the true ground, and a lot of the noise has now become the ground. So I wanted to show you what the problem is we have with this data set. It has excessive amount of low noise. You see that? Noise below the real surface. What happens with the sensor is a receiver. It's receiving the signal that comes back. When you hit the ground point, you get a very strong signal if it's an open ground, a good reflective open ground. You get a very strong signal back. What happens in the physics of the sensor is when you get a very strong pulse, you have a ringing after it, a little bump right afterwards. And I can show you later on, you can see those bumps. And those bumps are always 2 meters below the ground. And that's exactly what we're seeing here. So, between you and my explanation, everything makes sense now. What is really bad, I never tried this data set because I just finished it last night, and I don't have a pipeline set up for processing this, like a noise removal pipeline. However, let's turn this into an exercise and see if LasTools has the capability to first identify these noise points before we do the ground classification. And there's a tool called, I haven't used it all that much, but one of my vendors uses it a lot, called LasNoise. And LasNoise tries to find isolated points. And in order to save the day, we did get a decent classification of vegetation, but the ground classification is really terrible because it is below the ground. This is not useful. We can measure how deep it is below the ground. We can very quickly visually measure it. There's a funny option that I left in LasTools. If you right-click the menu, where's my zoom? Here it is. The menu, there's something called drop lines. So you can hang a line from every point. So I'm hanging a line of 50 centimeters from every point. And then you already see you have a measure of scale, in your point cloud. So 50 centimeters is not enough. They are definitely deeper than 50 centimeters. So I'm hanging a drop line of 1 meter. Yeah. So they are, maybe 1 meter, 1 meter 50, 2 meters below the ground, these points. Like this one here. That has been classified as ground. Oops. Oh, that's not what I wanted to do. If I press I can get the information about these points. Okay, so you see we're doing really unscripted, completely unscripted workshops here. There's nothing prepackaged about it. And it's cutting edge stuff because with the ringing and the explanation and everything. So now we'll try to go back a few steps and create one more last folder, one more tile folder that we will call view, that we will call tiles denoised. This one here. So now before we do the ground classification, we have to remove that noise. Wow, toi. I've never done that in a workshop before. Hardly ever did it myself before. So let's see where we can get. We should try with one tile first. That's what I usually advise, you know. If you try a new workflow, don't run it on all tiles. Use a small example tile, and we will use the same tile as we just did to see if you get something reasonable. So LasNoise is a tool. We load now. We go back to the raw tiles. I will load them all so I can pick the right one. I'll pick this one. That's the one we looked at, right? And now I say selected file only. I want to only process this file. And I want the output to go into the new tiles denoise directory. So what does LasNoise do? And we will have to play with the parameters a little bit because I don't really know them right now. LasNoise will maybe have a look at the README. So LasNoise looks for isolated points, and that could prove quite effective. It looks for points that don't have too many neighbors around them. For that, it puts a three-dimensional grid over all the points, a 3D grid. And the 3D grid size is, you set the size of every 3D grid cell with step. And then you say, in this 3D grid cell, every grid cell will have 26 surrounding grid cells, 27 in total with the 3D cell in the middle. So for every point, it will count the total number of points in all the other grid cells that are surrounding it. And if the total number surrounding is less than isolated, then it is considered an isolated point. So now, remember, we have to go back. We saw that our ground points are about 1.5 meters below the ground. Maybe sometimes only 1 meter. So we must set our step size small enough now. I would say set the step size to 0.5 meter so that, you know, if I go 0.5 meter up and another 0.5 meter, I hopefully don't have any ground points in there. And furthermore, how many other isolated points do we allow next to them? And that's a bit of an experimentation now because I don't really know. But a few iterations should get us somewhere where we see, hopefully this classifies the right amount of noise points without removing too many other points. That's also the challenge, that we don't want too many points in the trees to also be classified as noise. Also, we may be able to fix that later a lot easier to make them unnoise interactively. Anyway, I said this is a bit of a challenge now. One thing more, we can do that separately. We can do a step in XY direction and give it a different step size than in Z direction. So maybe we want to make the Z direction more fine-grained than the XY direction. So how about we take a Z direction of 10 centimeters and an XY direction of 0.5 meter, just to get started, and then allow how many isolated points, how many other points in that surrounding? It is not exposed. I told you sometimes it's not everything exposed in the menus. So the separate step directions are not exposed. So let's just write here 0.5 meter in that current step direction. And let's say if there are 3 other points or less, then they're isolated. I'm not sure if that's going to work yet, but we have to start somewhere. The isolated points will then be classified with classification 7. That's exactly how it was in the original data. All the noise points were classified as 7. Let's run on this one tile. Now It's important that you have only one tile here. We don't want to run on all of them. And now we want to change this here. And we have to change this in the command line because the option in the menu is not there. So we said we want to have a step xy, small xy. So I just added an underscore, an x and a y in front of that. And I specify my z step now explicitly. Minus step underscore z 0.1. So now this three-dimensional grid will have a spacing of 10 centimeters in the height and on half a meter in xy direction. So it's like a cube grid that has been squished. Now I'm just going to run this and have then a look at the output. Oh, it would have been useful to name the file something that indicates which parameters we have used. Usually I use odix for that. So then if I create multiple files and then I compare them later on, I know which parameters I used for which file. It's completed, and now I go and have a look.
It took a little bit too much.
Huh?
It took a little bit too much at noise.
It took too much?
Mm-hmm.
Oh yeah.
The entire forest, for example.
Well, what we do know, let's have a closer look. Yeah, well, we could have thought about that a little bit. Let's see with the ground points. Well, definitely all the points below the ground are now noise points. Yay! What's the only problem? Actually, it might not be a problem, because we can fix that. Because we don't need to use these points for ground classification. You see, all these points that have been classified as noise could not possibly be part of the ground. Well, they could, but let's assume they're not. You know, because if I turn them off, if I say only unclassified points, oops, huh? That's strange. Usually when I say give me the unclassified points, render only unclassified. Why doesn't it show any points now? That's strange. How can I turn off the noise points? Show only the noise points. I think we have, this might be a reasonable solution. Because what we can do, we can do this kind of classification. It's kind of almost a ground detection algorithm, because everything that doesn't get classified seems to be on the ground. And afterwards, once we did the ground classification, we can say everything that's above the ground classified to unclassified. And what's below the ground, the below noise points, will not get reclassified. And because we have modules for all of these steps, we can put together a pipeline that achieves all that. But maybe before we do that, let's try one more setting for last noise that maybe has, because I'm not entirely sure we do have all the ground points. So let's do one more setting. I'm renaming this now, this file, to remember the settings. I'm renaming this to XY was 05. Oh, there's 05. And Z was 01. Just to remind myself what this was. And now, before I go into the coffee, I create one more version. I just say run again. And now I'm creating a slightly different version. Any suggestions? Underscore XY minus step 0. I would say I go with step 0.2, and maybe I make my XY step, I increase that to 1 meter. like this. And maybe yeah. And now I already...
Have a step set.
Oh, very good. It was just a check if people are paying attention. Okay, so step Z is 20 centimeters, step XY is 1 meter. And let's run this. And I renamed the file, so I should be safe not to overwrite the other one. And let's have a coffee break now while this is running, and hopefully we manage to fix that data set somehow. So assuming you still have LasNoise open, before we were running just on one tile to experiment and have a look. Now I would like you to select process all files. And in your case, run on 2 jobs. I'm not actually going to run mine because I already did run it. The output should still go into that directory. If you have your program still open, then you don't need to change that. It was LasTools, it was the tiles denoise directory. And then the rest we need to type in the command line. Because I told you the options step X, Y, and step Z separately are not in the menu yet. But I think I should put them in the menu because I now realize myself that they are quite important. So you should have this command line. Zoom in one more. And we need to change the step to step XY. So we have a different step in XY direction, and we want to put this to 1 meter. 1. And then we must also add again, you can always put an extra space. Just don't put any spaces at the wrong, no space here. The minus in step must be 1 word, and there can be spaces here, but they need to be separated otherwise. And then minus step underscore Z, that's the step size in Z direction, and we will set that to 0.2, meaning 20 centimeter. And again, there needs to be spaces around all of them. And then the output should go into that directory, denoised, and it should be compressed. And I told you I'm not going to start it because I already have the result. So if you could start that, and then we can inspect some of the results. So I show you the results we will get. This is in the denoise directory. And let's just look at one of the tiny files. Right on the water. What do we get on the water? Well, sorry. I select this mode where I can get a profile view. And all the pink points are the ones that are classified as noise. And I make them bigger. So those are all the points that are farther away from somebody else. And the black ones are the ones that are considered ground. In this case, the ground is the water surface. So that looks pretty good. Looks like we found the right settings to get the isolated points. If we look over here at the very end, at the edge, you will see this. Well, we're at the edge of a survey above water. It doesn't really matter what happens here because this data is kind of crappy anyways. It is surveying on top of water at an angle. We never really know what we get here anyways. So the spacing between the points gets bigger. Hence, our isolated filter also considers them as isolated. But that's fine if it happens here. Now let's look at another area. That this one here. This seems to be if I change the coloring, it becomes more obvious what this is. This seems to be the tip. So let me select some interesting area, like here, and switch back to color by classification. And now I expect to have a lot of wrong classifications up in the vegetation, but that's fine. If it's above the ground, I can fix it later using another trick. If it's below the ground, and here I still have an issue. If it's below the ground, it's a problem. Here is one below the ground. You see this one guy? This one. I didn't get this one. But if it happens only occasionally, it's fine. Last ground is actually usually sufficiently robust against occasional low points. But this was just too many, and it basically formed a ground surface. But you see, most of the low points are now classified. We could use this as an exercise to now, fix like this one here. But I don't really want to go into manual classification. You could do it. Oh, one thing I want to point out, look at how all the high points here have also been correctly classified as isolated points. For this course, that's good enough. Let's see what we get when we use this kind of noise and exclude it from the ground classification. So we tell last ground, do not use these points to try to make them ground, because we know they are below the ground, and if you use them, you will be led astray. So we want to delete our current tiles that are ground. Whatever we did before, they will be overwritten anyways. But I just want to make a point. We're not going to use those. Those were bad. So I delete them. Tiles ground, I made it empty, the directory. I will create new ones now. And so we have to go back to last ground. And this time we start last ground from the denoise tiles. We starting from the denoise tiles. Starting last ground, and I'm browsing for the tiles that are denoised. Tiles denoised. Last time we started from the raw tiles. Looks the same. And now there's one more important option we have to do. We classified our points as noise points, but now we need to tell last grounds to ignore these points from the computation. And if you look at the menu, there is something to do so. It's called ignore points. And you can select a point class here. And by the way, I'm coming at night to shine a flashlight in your face to ask you what classification ground has. If you would be an advanced LiDAR course, I would ask you a whole bunch of classifications. And here they are all listed. Not all of them are frequently used, but the low vegetation, medium vegetation, high vegetation is common. Building, water, overlap, and the noise. Those are the typically used ones. So number 7, that's what we classified this as. So we want to ignore points that have the classification 7. Again, we want to compute the height. And we need to select the output directory. This will now go into the tiles ground directory I have just emptied. Tiles ground, use current. And maybe one more thing, I want to run on more than one core. In my case, I run on 7 cores. You should run on 2 cores. Oh, and I again go for ultrafine in the granularity settings here. And now I need to close some of the menus so I see my run button again. Anything unclear? There was only one difference now, and that was ignore points was set to low noise. That's the only difference to before. So let's look at the command line. Last ground, list of files, as always, now are the denoised files. 7 cores, you should have 2 cores. City, ultrafine, ignore the class 7. Oh, that's a new one. Everything else is identical to before. And let's hope we do better. We need to do one extra step now. Okay, so I delete the classified tiles. I mean, with LasTools, there are really many ways that lead to Rome. Many different. So I try to right now find the way that is the least amount of processing steps. And we could have unclassified the noise points above the ground, but we may not have to. So let's use LasClassify as the next step. Again, browse, browse. And now we start from the denoised and ground points. But before we do anything, we should have a look that we have, hopefully you have better ground classification now. Knock on wood. Selected file only, and I start the viewer on the same file where we had this horrible ground classification before. Does look a lot better. So if I now press G like ground, yes, I have the ground. And if I inspect it, of course you will see now also at the boundaries we will have errors, because at the boundaries you have fewer points on the other side, so some of the ground points have been classified as noise now. Because if I put a box around them and on the boundary half the box is not there, these points have a much higher chance to be considered isolated. But the boundaries we don't really use because they will get cut off later on. It's another reason why we use buffers. Voila. Looks much better. We have a lot of noise points under the ground, and the ground surface is nicely defined. Never do a workshop with data you don't know.
Survival.
So I tell it process all files. I output now to the classify directory, tiles classified. And anything else, run on more than one core. I run on 7 cores, you run on 2 cores. Quickly review of the command line. We should have the ones, the ground classified ones. I hope I checked the compute height. Did I? Because if you didn't check it, LasClassify will not work. It needs the height above the ground. And there was a check button in the last step of last ground called compute height. You can check that just by running LasInfo, because it gives you a min and a max value for the user data, and the height is stored in the user data field. And if that user data field shows min is 0 and max is 0, then you don't have heights. If min is 0 and max is 255, then you should be good. Or you can do the histogram to see even more information. I already know that the next step I want to run LasHeight. So I'm starting for the height normalization. So I'm starting LasHeight. And I'm loading the classified points. And now I basically want to have a look. So I say view only one file, go back to that one file that we already know fairly well, and view it. Well, looks a lot better, but yes, the noise points are still in there, which is not so nice, but this can also be fixed with LasHeight actually, even at this stage. But what's very nice is to see all the noise below the ground is also still noise. And that is supposed to be noise. But some of the very high noise has now been classified as vegetation because we didn't use the noise as, we didn't exclude the noise from LasClassify. Let's have a closer inspection of our buildings. So maneuvering can be a bit tedious with my silly interface, but you get the hang of it eventually. So, now there's a lot of noise points in there which maybe shouldn't be noise points, like this side of the building here. But all in all, the main roofs are found. A lot of the time, these roof computations are used for finding areas which have a good solar potential to create solar catasters for installing photovoltaic. So it's actually, for these applications, it's actually good that these kind of things are excluded and only the big plains are found because you can't install a solar panel here anyways. So in a way, what you may think, hey, it didn't classify the full roof, sometimes it's actually a feature because you don't want to classify those things where you can't install anything as a roof. Even so, it may be a roof because you're really interested in the planar sections of the roof. And for that, LasTools is very widely used with some of the very big solar power installing companies and the companies that consult people where to install solar powers, because it is very good in finding suitable roofs in a completely automated manner. Well, not suitable roofs, flat roofs where you can install something. The suitable roofs you find, and that's a completely aside, you find by making a shadow calculation, simulating the sun and simulating surrounding buildings and checking how long the roof will actually be in the sunlight. There are several factors that prevent it from being in the sunlight, like a mountain next to the house, other houses, a big tree next to the house, or just the angle of the roof towards the sun. So, but in order to do these calculations, you need to know where the roofs are and which directions they're pointing and at which angle. Okay, so that looks pretty good. What we do now is a height normalization step. And as we do the height normalization step, we will also, and just because we can, we also will classify all points that are noise points back into being unclassified if they are above the ground. So this is LasHeight. LasHeight computes the point of each LiDAR point above the ground. We actually have this already stored in the user data field, but only in approximation. Height normalizing the LiDAR means I'm taking the elevation data, the elevation value is stored as a Z coordinate of every point. It says the elevation above the ellipsoid or the elevation above the geoid, depending what kind of datum I'm using for the elevations. Do you know the difference between the ellipsoid and the geoid?
No. Yeah.
The ellipsoid is a mathematical approximation of the Earth as a perfect mathematical thing, like an ellipsoid. And it's very nice for computations, and the GPS operates on it and everything like that. However, if you want to make calculations of how the water flows, this mathematical construct is not very useful, because things that are, the elevation is not based on the gravitational field of the Earth. And for how water flows is very much based on the gravitational field of the Earth. And if you look at where is zero, or where is the same gravitational field on the Earth looks more like a potato, like a shrumpled up potato, than an ellipsoid. It's not, so there's something called autometric heights, and those are basically height above sea level at every given point on the Earth. And that changes. If you are on Mount Everest, the gravitation is different than if you are on an area where you don't have so much land mass below you. So to be on a geoid means you are on the place where water really flows the direction of lower elevation. And when you're on the ellipsoid, you have a nice mathematical way of expressing elevations, but it has nothing to do with the fact how water flows. That's sort of an intuitive. And people go back and forth between these two representations because both are useful. The ellipsoid is more useful to distribute data in because everybody knows it, and the geoid is more useful locally when you are at a place, because locally it's important, like that basically on the ellipsoid, water can flow up the mountain if you use the elevation values, and the geoid will correct that so the water really flows down. You can also do a geoid transform with last height by using an external geoid information. And that you see that right here. So now we compute the points above the ground, and we replace the elevations with the height above the ground, and anything that is above 0 meters. Let's make it anything that's above 1 centimeter. Just to be sure, no funny things happen. We will classify back to unclassified. But now we must do one more thing. This will classify everything, houses, vegetation, everything. We also must make sure, stupid floating point. We must make sure to ignore the things we don't want to lose. So we don't want to lose the buildings, and we don't want to lose the vegetation. And I only computed high vegetation. Sometimes, so the classifications would also be zeroed back to unclassified if I didn't put this there. We just spend a lot of time computing them, so we want to make sure that they do not get classified back to unclassified. Only the noise points will. And only the noise points that are above 1 centimeter. Maybe make it 2 centimeters. This is a problem of a floating point error, round off. Oh, and I want to process all files, and I want to put the output into the normalized directory. Tiles normalized. And that's, hopefully, the last thing we have to do with the LiDAR points for the time being before we can start to produce derivatives. Run. So, on all these files, we classify everything above 2 centimeters back to the unclassified class 1, but we ignore the class with the buildings and we ignore the class with the vegetation. We put it into this directory, and now I forgot to say how many cores I want to use, so I just add it here, minus cores 7. And this will height normalize the LiDAR. all ground points will have height 0. And all the other points will have a height relative to 0. So vegetation height will sort of measure the height of the vegetation above the ground. Oh no. Not again. So what do you do when this happens? First you repeat it a few times, and if this happens regularly, you send a message to Martin or to the LasTools group, which you join, and you explain exactly what you did. You give a LasInfo report, and you run the option with minus verbose, so it prints more, and you copy whatever is in the black window. I didn't run in verbose now. The black window is this one here. Maybe it worked anyways. Somebody told me about this error before, and I never had this error. Maybe now that was my first time. Details normalized. I don't know. Looks good. Looks like I have them all. Might have been in the cleanup phase there was an error. So what did we do in the last step? We height normalized it. So if you look at the ground points now, here are the ground points, and I press T, and I triangulate these ground points, T, I get a very, very flat surface. And anybody who is a... Did I get a flat surface? Yes. So a geologist will be absolutely shocked now because everything he's interested in is gone. All the features of the terrain, the fault lines, you know, the erosion patterns, they're all gone. Everything is flat. You see the triangulation, but they only triangulate points, and all the points have elevation 0. Or in this case, it means height 0. But if I'm adding the other points, like the vegetation points, they now have a relative vegetation based on the height above the ground. So let me untriangulate and show all points and look at a cross section. So in these cross sections now, I basically can now query these trees. Let me zoom in a bit more. I can now query the tree tops, ++, for their height. And if you look now here, the Z coordinate corresponds now to the height of the branch above the ground. And I can basically pick the tips of the tree and ask it how high they are. So this is 25 meters. This one is 26 meters. This one is, I'm pressing I in my keyboard. I should maybe say that I like identify information. And this one here may be a noise point still. I'm not sure, maybe there was a little bird flying above the tree when it was scanned. Or was that tree that high? Is there maybe some, oh no, maybe a part of a tree, because there's a bigger tree there. So that might not have been a noise point. But I'm sure there's some aerial noise points in there. We can now remove them by running LasNoise again, but not now it's much more conservative settings. Now we will run LasNoise saying, you know, anything that is a 3 by 3 meter box and there's nothing nearby, there at least when there is only one other point nearby, then it's a noise point, for example, in order to remove very robustly only those points that are clearly outliers. And that is needed in order to make a nice CHM as well as a nice DSM. We did a lot of noise removal already, so we had our noise removal exercise, and we don't need to deliver this data to a client. So that's why I just tell you. I would run this through another last noise with a bigger step size and then visually inspect it again to make sure these individual points that you saw earlier that are really high up will get removed. Okay. Whew. So the LiDAR processing, meaning loading LiDAR points, processing the LiDAR points, and generating a better set of LiDAR points with some additional information in them, that we have completed now. The next step would be to generate derivatives from those LiDAR points. Raster derivatives will be our first target. So let's start with generating the DTM. For this, we use the tool LasTools. The tool I already mentioned is LasTools. You could use BlastToDem, but there is no reason to. These are small tiles, and LasTools works quite fine on them. I should mention that BlastToDem starts up 3 processes under the hood. So it may be beneficial if the data set is smaller to use LasTools because that's only one process. Which file do I open now? Normalized would not be very good because we would create very boring DTMs. Totally flat, everything 0. Our options are tiles ground because we're only going to use the ground points now, and the ground points are already existing in tiles ground. They are also existing in tiles classified. We haven't changed them. So you could use either of the two. It doesn't make a difference because the only points we use are the ground points. And the ground points exist in both of these. I'll use tiles ground. I don't really know what the point density is. I haven't really done a quality check. So I don't know what is the best raster I can generate. But remember I told you once this little trick where you run LasView, selected file only, LasView, and I turn it into LasInfo. And the option to play music, you remember that one? Minus CD, minus compute density. That computes the density, just sort of a rough average to give you an idea. And if I run this, then in the black control window, it will quickly give me a rough idea of what the point density is. So and knowing this is very helpful for making an educated choice about the spacing, the ground spacing. So here we have the point density, all returns, last only. So we have 6 points per square meter. Now we should keep in mind, a lot of that has to do with the overlap. There are overlapping flight lines in there. So I think maybe I have 4 points per square meter. So not all of them are ground points, but a lot of them are ground points because it's a fairly open area. So I could go, for a fairly detailed DTM here. I could maybe make 0.5 meter. But that will just create a lot of data. So I think we could do 0.5 meter DTM here. We have 1 by 1 kilometer that creates 2000 by 2000 pixel images. That'll be a lot of data to load and look at. So let's stick with 1 meter. In this step, we will actually create real DTMs, not hill shades. So we leave it at actual values. And in this case, the output we generate, for example, TIFF is a nice format to store. You can store both images to look at, but also elevations in the TIFF format. Now I want to process all files. And the very important thing now is this option. Use tile bounding box. That's super important. So far, we've been operating with a buffer around every tile. You see these tiles are overlapping. If I don't check this, I will create rasters that go all the way to the edge of the buffered tile. But all along I told you, in the buffer, at the edges, it's bad. That's where the errors happen. So what will happen now is I'm cutting off the edge. I'm only rastering the 1 kilometer by 1 kilometer of the original tile, and the 25 meter buffer around it, I ignore, because that's where the error is. One thing I shouldn't forget, very important, I want to create a DTM, so I should only use the ground points. So I filter by classification and keep only the ground points. Keep classification 2. And in this case, I don't think I need to filter with the grid because I just have about the right amount of points. I mean, not that you ever need it, it just removes, lowers your memory footprint. This looks all very good to me. Oh, the output directory. Almost forgot this. So we output it into the, no, not there. Into the DTM directory. Somehow I just lost power. Somebody's feet were hitting my power supply. Whose feet could it have been? But I think I can start this. Tiles DTM. So let's review the command line. And I hope you have the same command line like me now. LasTools, list of files. There should be either ground or classified tiles in here. We keep only the ground points. We raster the elevation. This is the important one. Use tile bounding box. This cuts off the buffer. And we output it into this directory in the TIFF format. Oh, I forgot the cores. Oh, now I'm gonna do one after the other.